Okay, everybody, go ahead and pause this video and read this problem. Basically, what we're going to be going over is how the different parts of heat transfer change as you move through a non-uniform body underneath these conditions. So the larger area, the lower temperature, and so on and so forth. So pause the video right now if you want to read that problem, and I'm going to go ahead and get right into it here. So moving on with this. So we know that for the very first part, we need to find out what Q is as the area changes and the temperature moves on. We know that it's a steady system, well, fairly steady. The temperature is the same on both ends. And okay, so the following. So we need to find out if Qx is increasing, decreasing, or staying the same. Well, Qx is the heat transfer, so we know that it'll follow the heat transfer law, or the sum of the laws. The heat in equals the heat out. Just do that. First law of thermodynamics there. Energy stays the same, so on and so forth. Sorry, I don't know what it is. But, so we know that the energy in equals the energy out. So we know that the Q in, which is the heat transfer in, has to equal the heat transfer throughout any area. So we're going to say plus dx right here. So at any x value, however far you are down this, I'll draw the truncated cone here. You know that no matter where you are in this, the same amount of heat has to be traveling through here. So we know that Qx by the conservation of energy is going to remain constant. So, and is independent of x. So we've got that first part right there because of the conservation of energy. But as the area increases, you know that Q double prime, the heat flux, which is the heat transfer through an area, which is equal to Qx over Q, Qx over A, that is going to change because as the area increases on this cone over here, the heat flux is also going to decrease because as this number gets larger, this number gets smaller. So we know that Q flux, the heat flux, is decreasing. Decreasing? So we got that right there. So that's pretty easy. So now moving on, we know that T decreases. T is decreasing. T is getting smaller as we're moving down here. It's increasing x. Okay, so let's see. What was the other value we had to find? Excuse me. Okay, so K. For K is typically a material property, so that it shouldn't change generally. But we know that in this situation, K is equal to the equation K naught minus A T, where A is some value. A is just some constant, and T is changing. So if we think of T, we know that T is getting smaller as we go on. So up at the top, T is at its full value. K is as small as it's going to be. But then as T gets smaller, the subtraction from the original K gets smaller and smaller. So K actually becomes larger as temperature as you move down the cone. So in this case, because of this relationship, K is actually increasing with increasing x. Just like that. And box all of these correctly so we know what's going on. And for the final part, we know that, okay, so we need to find out if dt over dx, what it's doing within the change of stuff. So this is actually pretty easy because you have a delta t over delta x. We're going to just go ahead and ignore the top. We know that temperature is decreasing as you go down, but we also know that x is increasing. So these two taken together, you know that as this number gets smaller and this number gets larger, the entire ratio is going to get smaller. So we know that dt over dx is decreasing with increasing x. So none of them is constant except for the Q of heat rate because of the energy, or the conservation of energy. So it's constant. the flux through the area is decreasing because the area gets larger, making the flux through the area smaller. And because of this relationship, K is increasing, but normally K is a material property. And then dt over dx is decreasing because t is getting smaller and x is increasing. So there you go.